Okay, today we are going to move on to the next chapter, which is about the risk assessments. Chapter 2, risk assessment, and we have two learning objectives today. Learning objectives includes the first, understand risk assessment process. Second, compare toxicity. Third, calculate the risk. All right. So, in environmental engineering, risk assessment process include environmental risk assessment process include first, we need to first identify hazard. So hazard identification is the first step. So when, for example, um, a chemical company develops a new chemical for consumer products, then we need to identify whether this chemical has a will pose any risk to human health or not, right? So it'll be about the toxicity. Determine whether the chemical has a toxicity or not, right? And then the way that we do this toxicity analysis include two steps. The first, those response assessments. Response assessments. And in this step, we determine whether the contaminants or toxicants pose any acute or chronic toxicity. Mm-hmm. Acute toxicity or chronic toxicity, or whether we need to determine whether a chemical has any carcinogenic effect or not, because carcinogens are classified into whole different class of chemical. And on the other hand, we also need to evaluate the exposure assessment, exposure route, exposure assessment. So, for example, in this step, we evaluate the exposure routes, whether a chemical will be exposed, individuals will be exposed to oral ingestion or inhalation or dermal exposures are expected or not. And also, we need to take age into consideration, and we also need to consider whether there is any synergistic effect or not. And after identifying hazard, we need to do those response assessments and exposure assessments. And with this information, we can characterize risk. Right? And then, so we summarize the data that we got from those response assessment and exposure assessments. And then we can come up with a solution, how we can manage so in this step we can determine what to do, decide what to do. So these are the risk assessment process. All right, let's talk a little more about those response assessments, talk a little bit more in detail about this. And also, yeah. So, no, actually, we need to talk about the hazard identification first. So we are going to talk more in detail about hazard identification and those response assessments. Hazard identification. Hazard identification. A toxicity or toxic chemicals can be classified into two classes. Whether the toxicity is acute or chronic. Acute toxicity is defined as the toxicity that is pose immediate response. And after exposure. And there is this parameter that we use to compare one toxicant to the other, which is LD50. LD50 is defined as is short for lethal dose at which 50% of the exposed population is killed. So LD50 of different classes of chemical, based on the LD50, the chemicals can be classified into several toxicity ratings. First, if the lethal dose is larger than 15,000 milligram per kilogram body weights, and the chemical is considered as practically non-toxic, and example is sugar, right? And if the lethal dose is less than 5 milligram per kilogram body, then the chemical is considered to be super toxic. And for average adults having like 70 kilogram of body weights, 50% will be died by by being exposed to less than 7 drops of these chemicals. And these chemicals include dioxin. And yeah. And this LD50 is defined differently. The LD50 number, A1 toxic chemical has different LD50 numbers depending on the exposure routes. So, for example, oral exposure LD50 the chemical toxicity can be, classified uh, from category 1, which is super toxic, to all the way to category 5, 5,000 milligram per kilogram body weights. And if the LD50 uh, through the oral exposure is less than 5 milligram per kilogram body weight, then it is considered as super toxic. Yep. And the based on the dose response assessment, acute toxicity is typically have these types of plot. So chemical on the graph on the left side, chemical A and B. When we have these two chemicals and we do this, dose response assessments and got this data, we can safely say that chemical A is more toxic than chemical B. So here, keep in mind that lower LD50 means more toxic, because low LD50 means that lower amounts of chemical can kill 50% of the population exposed to the chemical, right? And if we have these two chemicals having the dose response data as shown in the graph on the right side, it'll be a little tricky to determine whether, which chemical is more toxic or not, because, at lower dose, chemical C poses, a higher toxicity, and chemical A is more toxic in higher range. All right. So that's about the acute toxicity. And chronic toxicity. There is another type of toxicity, chemicals that have different um, types of toxicity, which is chronic toxicity. And chronic toxicity is responses that are diagnosed after prolonged period of exposure. And the example of these chemicals that have chronic toxicity include mutagens. And mutagens are class of the types of chemicals that cause DNA modification, mutation. And it can be subcategorized into teratozin, which affects fetus, or carcinogen, cause cancer, that cause cancer. And there is this, one hit theory about these carcinogens or mutagens, one hit hypothesis. It is very important, which means that this is something that I talked about at the first lecture, which means any exposure to carcinogens or mutagens, leads to non-zero possibility. That a malignancy results. Malignance results. And malignancy is invasive tumor. So any DNA modification has a non-zero possibility that can become cancer, right? Invasive tumor. So there's no thresholds. There's no threshold for mutagens. Okay? So, being classified as a carcinogen or mutagen is a really serious, So people in who get to determine whether who do this the risk assessments take extra care to classify a chemical into carcinogens or not. So, for example, there is this table that the researchers use to whether we can decide a certain chemical is carcinogen or not. And first, according to the EPA classification, carcinogens can be classified into 5 groups. First one, a certain human carcinogen, group A, 100%, right? And group B is probable human carcinogen. Group C is possible human carcinogen, and group D not classified, and group E is there's no possibility that this chemical can cause any cancer, right? So let's take a look at the table 4.8. The way that we read this table is that when we have to take a look at the first line, which is animal evidence. So when we have sufficient evidence from animal experiments, even though we have 100% evidence showing that a certain chemical is should be classified as a carcinogen from animal experiments, if we don't have enough human evidence, like for example a second line on the first column, when we have limited human evidence, then it is classified as probable human carcinogen, right? So it is a little leaning, this table is leaning towards to the industrial benefits, not the consumers' benefits. So yeah, it is, I think it's supposed to be the other way around, but anyway, that's how a carcinogen is a chemical is classified as carcinogen or not. So next topic is about oops 2.1.3 toxicity testing. Typically, toxicity testing is done on animals, not on humans. And there are two different types of experiments being done on animals. One of them, the first one is in vivo. So doing the experiments on the animal directly. So short-term acute toxicity is being evaluated with this animal testing in vivo animal testing, as well as long-term chronic toxicity is also evaluated by these in vivo animal tests. And sometimes the experiments is done in vitro with the cell, right? Such as carcinogenesis is done on in vitro animal experiments. And long-term chronic toxicity includes carcinogen. And we're not supposed to do this toxicity testing on humans, but we can evaluate the toxicity by studying the victims of tragedy, which is also known as epidemiology. So the way that we do this analysis is that we prepare this table. Um, So we first divide the whole population into two groups: exposed population or unexposed control population. And the monitor whether and to see if there's any population to got the disease with the disease or without the disease. The population that got the disease or not got the disease, and count the number A, B, C, D. And the first parameter that we can determine based on this analysis is relative risk. Relative risk can be calculated by getting the number of population that got disease after being exposed. The number of the population that got the disease out of the total population, that was exposed to the chemical, and divide the number by C plus D. And if this number is larger than 1, then it is considered as toxic. And the relative risk explains the risk of developing the disease given exposure. The second parameter that we can calculate from this analysis is odds ratio. Odds ratio. These numbers are pretty much, meaning pretty much the same. So AD divided by BC. And also, so basically, it is about A divided by B divided by C divided by D. And if this number is larger than 1, it is considered as toxic. And similarly, there is another parameter that can be calculated, is attributable risk, which can be calculated by A divided by A plus B minus C divided by C plus D. It's similar to number 1, and the criteria is not 1 but 0 because it is, subtract. So if it's larger than 1, then it is considered as toxic. Okay. All right. So the next topic is about dose response assessments. This is the most important parts. It is about chronic toxicity. For acute toxicity, we have LD50, right? And for chronic toxicity, we calculate these dose response assessments for long-term exposure scenario. So dose response assessment is about mathematical relationship between the amounts, the dose, the amount of toxic, amounts of toxicant and the risk. And based on the one hit hypothesis, there's no thresholds. So the risk against the dose will start from 0.0, and the risk will increase as the dose increase. And we can calculate the slope from these experiments, animal experiments, right? And there are two factors that can be obtained from these experiments. The slope is PF, potency factor, and dose is basically CDI, chronic daily intake. And CDI here is average daily intake which have a units of milligram per day, and divide by body weight. This is CDI, kilogram. So the unit for CDI is milligram per kilogram day. And potency factor, PF, potency factor is typically given in a table. Take a look at the table 9 in the textbook. It is basically incremental lifetime cancer risk divided by chronic daily intake, CDI. Therefore, the risk is CDI times PF. Let's see. Do I have the table? Yeah, here's the table 9. So chemical, for example, arsenic is category A, which is like 100% carcinogen, and potency factor is a potency factor through oral exposure is given as in 1.75 milligram per kilogram day. I mean, to the -1. And inhalation route exposure potency factor is much higher, right? So let's take an example. All right, this is example number 2 in the textbook. Risk assessment for chloroform in drinking water. So when a drinking water is disinfected with chlorine on undesirable byproducts, chloroform can be formed. And let's suppose a 70 kilogram a person drinks 2 liters of water every day, potable, the tap water, every day for 70 years with the chloroform concentration of 0.0 milligram per liter. This is the drinking water standards, and calculate the risk. The first, find the upper bound cancer risk for this individual. So from this table, chloroform has this oral the potency factor 6.1 times 10 to the 10 to the -3, right? So example, potency factor is what? 6.1 10 to the -3. 6.1 times 10 to the -3 milligram per kilogram day to the -1. And CDI, how much chloroform this person is exposed to, is 0.1 milligram per liter, and this person drinks 2 liters per day, and lifetime exposure is just a general assumption here, and body weight is 70 kilogram, so it is calculated to be 0.0200286 milligram per liter, no, milligram per kilogram a day. Keep in mind that the units for potency factor and CDI are, reciprocal. So the risk, the possibility that this person can get a cancer from the chloroform contained in the drinking water over 70 years of lifespan. The risk is CDI times PF and 0.00286 times 6.1 times 10 to the negative 3, and it is 17.4 times 10 to the negative 6. So what it means, let's take a look at the example closely. If a city with the 500,000 people, half a million people in it, also drinks the same water, and how many extra cancer per year would be expected, right? Then this is the possibility. So what this number means, over 70 years period, this number is the probability a person will get a cancer from chloroform. Chloroform in water, right? And it's 17, basically it is 17.4%. It is a possibility for a one single person, but it can be translated into 17.4 victims out of million. So number 2, for a city of half a million population, the person that will get a cancer from this chloroform exposure can be calculated by 17.4 times 10 to the negative 6 times 10 to the negative point 0.5 10 to the 6 half a million, and this is for over 70 years period, but the number that you were asked to calculate is per year, so we need to divide the number by 70, and the final number is 0.12 extra cancer per year, right? And what was the next question? Compare the extra cancer per year caused by chloroform in the drinking water, this number, and the cancer death rate. The general cancer death rate in United States is 189 per 0.1 million. So we can calculate for a city of 0.5 million population, 189 out of general cancer, the number of the population that gets cancer from any other types of, I mean, in general, is 945 cancers per year. So even though there is some risk by being exposed to chloroform in the potable water, that the, it is not that of a big deal compared to the general cancer risk. That's how we can interpret the calculation that we have in here. Okay. So, okay, let's you know what? Let's stop here because the next topic is a big chunk of calculations and the topic, and I'd like to talk in person. So, yeah, for today, this is it, and I'll see you on the Monday next week. Okay, bye.